Well, hi guys. We're having a look here at families of functions where f of x equals x to the n, and n is allowed to be any rational number at all. Rational meanings could be fractional, could be negative, could be anything, okay? I know, what a thought. Well, don't worry, Wolfman will fix you. Now, we know that y equals x to the n graphs all pass through the origin, of course, apart from reciprocals, where n is negative, in which case they're undefined, where x equals 0. But apart from that, they all go through the point where x is 0, and their shapes can be determined, actually, from the answers to 4 key questions. Are you gripped? Well, come on, here we go. Yes, but I should emphasise that n equals p over q, where p over q is any rational number in its simplest, irreducible form. Okay? Do you get that? All right, let's press on now and see what we get. Okay, question 1. Is q, the denominator, odd or is it even? That's very important, because if it's odd, then the graph will have both a left-hand side and a right-hand side relative to the y-axis, like aka little drawing there. Yes, if it happens to be even, then the graph has only a right-hand side to the right of the y-axis, including the origin. Now, an example of that would be y equals x to the half, right? That's the wrong shape for x to the half, but that's nevertheless the kind of thing I'm talking about. This one here, where the denominator is odd, would be something like x to the third. Again, that's the wrong shape for that, but you know, you get the idea, don't you? That's very good. Now, question 2 for me and you, is p, that is the numerator, odd or even, right? That is the next question we need to ask, because the plot thickens. If it happens to be odd, then we get an odd function. If it happens to be even, then we get an even function, right? Now, of course, I'm talking about, obviously, if the denominator was even up here, well, then this wouldn't apply. This is for odd denominators, right? That's for odd, because these guys only have a right-hand side anyway, so you can't get odd functions or even functions if they've only got a right-hand side to start off with. Okay, so if it's odd and the numerator is odd, you get an odd function. If it's odd and the numerator is even, you get an even function. That's what I'm trying to say today. Now, third question, is p over q negative or positive? That's pretty important, because if it's negative, you've got a reciprocal graph or a 1 over kind of graph, yes. And if it's positive, you go to question 4. And question 4 says, if p over q is positive, then if it's greater than 1, you've got a graph which we're familiar with, such as y equals x squared, that kind of thing. Yes, and if it's less than 1, but still positive, that is between 0 and 1, then you get this kind of thing, like the root x graph, y equals x to the half, yeah? That kind of thing. Now, this is probably all clear as mud, but I'll show you as we go. We've got some detail following here, and we'll see where we go. I'm just going to restate the fact, though. It's very important. In every case being considered, the approach taken depends on whether the denominator of the exponent n is even or odd. It's worth saying again. If the denominator is even, the graph only has a right-hand side. If the denominator is odd, then the graph has both sides of the y-axis and will be odd or even, as follows. If the numerator is odd, the function will be odd, and if the numerator is even, then the function will be even. Now, that's kind of like a restatement of what's on the previous page, but it's worth restating. And that's a big box around there to give you that grand summary of what you do with these things, yes? Here we go. Now we're going to look at the trend, because the trend is your friend. These are some odd denominator trends. Then we're going to do even denominator trends, and then we're going to go back to the odds to have a look at numerator trends. But anyway, just look at this. We won't get ahead of ourselves. That's the graph of y equals x to the 1, and of course the denominator of that is 1, and it is odd, okay? 1 over 1, odd denominator. There's x cubed, x to the 3 over 1, and there's x to the 5. You see what's going on here? There's x to the 7, right? Now, do you see the trend? Do you see what's going on? Pretty interesting, isn't it? Well, oh, look at that. There's x to the third. Goodness me. Okay, there's x to the fifth and there's x to the seventh. Now, that looks pretty beautiful, doesn't it? It's a work of art. However, there's great system, order and pattern in what you are beholding before your eyes. I'll show it to you. They all pass through 1 and 1, which is here, or they all pass through -1 and -1. I'm rattling off coordinates x and y there. That is, they are odd functions, but only for odd numerators, and these ones do have odd numerators. Okay, so I need to clarify that, but let's not get ahead of ourselves again. Okay, now x to the 1 over n, yeah, this is very, very crucially important. X to the 1 over n is actually the inverse or the mirror image about the line y equals x of x to the n. Did you know that? Okay, so x to the half would be the inverse of x squared. X to the third would be the inverse of x cubed, and so on. That's how it goes. If you're not sure, just go and work that out separately, and you'll see. Put down some function x to the n and then work out the inverse, and you'll see what I'm saying is true. Now, in this case, in this slide, I'm letting n be an odd natural number, progressing, so 1, 3, 5, 7. That's what I'm doing, right? Just to clarify that. Now, as n increases, right, the x to the n's, which are these ones here, on this side of the line y equals x, x bends toward the x-axis for this region here, where x is between 0 and 1, and away from the x-axis for x is greater than 1 up here, away from the x-axis. They start bending from the line y equals x. So these ones bend down from the line y equals x, and greater bending progressively as these numbers go up. These ones bend away from the line y equals x, starting from the line y equals x, as these fractional exponents, these numbers, the 1 over n, as those n's get bigger. It's pretty interesting, isn't it? And the reverse happens over this side of x is 1, when x is greater than 1, right? You get it? Pretty fascinating. There's some arrows to show you what I'm talking about, and there's the red arrows to show you what's happening on the other side of x equals 1 and on the other side of x equals -1. Okay? Getting it? Pretty marvellous, hey? Now, as n increases, x to the 1 over n, which is these ones over here, do the exact opposite. They bend away from the x-axis when you've got x between 0 and 1 in this region here, and they bend towards the x-axis here for x is greater than 1. And again, starting at the line y equals x, all right? That's what I'm saying. That's fascinating. Yeah, that's showing you that, and there's showing you that. All right, let's go over the screen now and have a look at some more of this fascinating stuff. Now we're going to look at some even tendencies. Now this is not an even anything. It's y equals x to the 1, but it's still a reference line. Now the graphs I'm about to show you, let n equals 2, 4, 6, 8. Now these guys do not have an even denominator, but I need to show you them first, because then I'm going to show you the ones with the even denominators, right? There's x squared, there's x to the 4, there's x to the 6, and there's x to the 8. Oh, my goodness, how amazing. Now, there's x to the half, there's x to the 4th, there's x to the 6th, and I haven't done x to the 8. X to the 1/8. I think I forgot. But you get the trend, don't you? My goodness, the trend is your friend. So what am I saying? The same trends as we observed on the previous screen for x squared to the 4th to the 6th and the 8th compared to x to the 1, 3, 5 and x to the 7. The same as we got for those odd functions on the previous screen, except these functions here, x to the 2, 4, 6, 8, are actually even functions, right? Where n in this screen is an even natural number, 2, 4, 6, 8. Okay, so what have I said there? I'm saying just look at these x to the 2, 4, 6, 8 at the moment, and notice that the trend, the way they bend down away from and under the line y equals x here, when x is between 0 and 1, and they bend the opposite way when x is greater than 1, don't they? And you can see by the fact they have a left-hand side over here, that the y-axis is a mirror image, and therefore they are even functions. That's all I'm trying to say. But what's more interesting is to have a look at these little beasties here, x to the half, x to the fourth, x to the sixth, and x to the eighth, and they are even denominators. You right? You got it? You're locked in? Of course they're even denominators, and so they're the ones I'm trying to focus on here in this screen. But the reason I had to do these ones first is because these guys are the image, the inverse. They are the inverse of the ones over here. Goodness gracious, the plot thickens. So what I'm trying to say is that x to the 1 over n is the inverse of the restricted function, x to the n, because I've had to make these restricted functions 1 to 1 because x squared, x to the fourth, x to the sixth, and x to the eighth are many to ones, right? You check out with the horizontal and vertical line test, you'll see they're many to one. So they don't have inverses, right? So if I want to get inverses happening, I've basically got to restrict the domain, and we restrict the domain to 0 inclusive up to plus infinity. So we take the right-hand side of these, x to the 2, 4, 6, 8, and then we can get an inverse, and the inverse is x to the half, x to the fourth, x to the sixth, and x to the eighth, right? Yeah, they're mirror images. It's beautiful, isn't it? The pattern is beautiful. So, right, let's explain that all right, I think. Now, therefore, I'm saying that x to the 1 over n only has a right-hand side, and that's why it only has a right-hand side if the n is even, is an even number, right? To the right of the y-axis, including x is 0. All right? Yeah, it's fantastic, isn't it? You know, when you get into it. Now, here's some odd denominators. Now, I'm going to look at the trends now for the odd denominators, and I'm going to keep the denominator the same and start varying the numerator, first odd and then even, and you'll see some amazing things to behold. So I'll show you. If the denominators are odd, just let me restate that if the numerator is even, you get an even function, and if the numerator is odd, you get an odd function, right? Now let's look at some odd numerators, and all these denominators are going to be odd, right, from now on. Now, that's my reference line, that's y equals x to the 1. Now, but let's go with these odd denominators. That's basically y equals x to the 1 over 7. 1/7, right? 1/7. Now, check in, odd denominator, odd numerator, but I'm going to keep the denominator the same now, and I'm going to vary the numerator with some odd numerators so that you can check the trend, which is your friend, of course. Now, so we might go with x to the 3/7. There it is. Hey, look at that. Now, do you notice, I'm just going to jump the gun a bit here, do you notice that as the fraction gets bigger on the numerator, in other words, the fraction gets closer to 1, these curves are moving, bending towards the graph of y equals x to the 1, which makes perfect sense. So what do you think the graph of x to the 5/7 might look like? There it is. Look, it just makes perfect sense, doesn't it? Yes, marvellous. I think it's truly marvellous. Now, I think I'm going to go x to the 9/7 now, because obviously x to the 7 over 7 is x to the 1, which we've already got. Yeah? But you can see that x to the 1 is in the same family as these little beasties, can't you? There's x to the 9 over 7, because that's on the other side, because that's now greater than 1, so that then resides on the other side of the line, y equals x. You know, the fractions less than 1, positive fractions less than 1 reside over here, the positive fractions greater than 1 reside over there, and the same trend continues. There's x to the 11 over 7, there's x to the 13 over 7. Isn't it beautiful? Now, of course, they don't look like, these three, the green, yellow and brown, don't look like mirror images of these ones over here on the upside, if you like, of the line y equals x, because they aren't mirror images, because we're not dealing with inverses here, we're just dealing with the trends. Remember, we kept the denominator the same, we're varying the numerator, okay? So I think that's what these notes will say. So for y is equal to x to the p over q, and p over q is between 0 and 1, what did I say? As p over q increases towards 1, the graph trends closer to the line y equals x, and that's what I've been saying. So I'll show you with arrows. There you go, right? Over here it's getting closer to the line y equals x, and down here it's getting closer to the line y equals x in that direction. Yes, good, isn't it? Okay, now what's next? For y equals x to the p over q, where p over q is greater than 1, the opposite effect's going to happen. So as p over q increases away from 1, greater than 1 and getting bigger than 1 progressively, the graph trends further away from the graph y equals x, and here comes the arrows. See? Yeah, these are getting further, continuing in the same direction but getting further away now as the fraction gets larger and larger. These improper fractions get larger and larger. Yeah? And the same corresponding thing happening over this side here. That's what's going on, guys. Now, that's pretty marvellous, isn't it? Now, let's do some even numerators. Now, this is really crazy stuff, as you'll see. Look at that. That is the graph of... Now, it's an odd denominator. It's an even numerator. So I'm going to go x to the 2, 4, 6, 8, 10, and so on, and you're going to see what happens. Now, you'll notice that I did say to you, look, up here, if the numerator is even, you'll get an even function. Well, I'm true to my word, ladies and gentlemen, that is an even function, because it's the left-hand side is the mirror image of what's on the right-hand side, where the mirror is the y-axis, yes? Now, let's do the next one. That's x to the 4 over 7. Now, see, the trend is your friend. The fractions are getting bigger towards 1, and the graphs are trending, getting closer to the line where y equals x to the 1. Yeah, isn't that true? Isn't that marvellous? Now, there's x to the 6 over 7, almost on top of the line, y equals x to the 1. And now we'll do, I think we better do 8 over 7 now. There it is, that's the pink one. Look, it's on the other side because the fraction is greater than 1. Yes? Beautiful, isn't it? That's x to the 10 over 7, and here's the 12 over 7. Now, that's going to be the end of the line. I'm not going to do 14 over 7 because that would be exactly 2 over 1, which... Yeah, and you can imagine what's going to happen if you do the graph of x squared. It'll just be a bit under that yellow one, but it's in the same class of functions where the denominator is odd and the numerator is even. Yes? Oh, it's so fascinating. Now, okay, so what have I said in my notes? So for y equals x to the p over q, where p is even, e.g. y equals x to the 2 over 7, denominator is odd, remember? Okay, this is equivalent to, oh yes, this is why you get the positive. But this is why this side is positive instead of down here like they were on the previous screens, like for, for y equals 1, x to the 1 over 7 or 3 over 7 or 5 over 7. This is different. These are even numerators. So this is equivalent to y equals x to the 1 over 7, according to your index laws, squared. Now, what happens, ladies and gentlemen, if something's down here in the negative land, in terms of y, if you square a negative number, it basically makes it positive. That's what happens. So that flips any negative little beasties that might like to be negative down here. If you square them or raise them to the power 4 or 6 or any even numerator, they basically go flying up here as positives. And that's why you get yourself basically an even function, because all the negative values of y, for y equals x to the 1 over 7, once you square them, they become raised to an even power, and therefore they can't be negative, in fact they are positive. Okay? Yes, I know, it's flabbergasting. So thus y is always positive and we have an even function. Okay, yes, the truth has been revealed. So then when p over q is between 0 and 1, what have I said here? There is, oh yes, when it's between 0 and 1, in other words, a positive fraction between 0 and 1, you get a cusp. See this blue? This is the really best illustration of this. This comes down here, flying down here, and then goes flying back up again there as the mirror image. But look, that's a sharp point there. That's on the origin. That's a sharp point. That's a cusp. And therefore the gradient is not defined for all of these little beasties here from y equals x for these fractional ones. So therefore, what we were talking about was x to the 1 over 2 over 7. That's right, 2 over 7, 4 over 7, and 6 over 7 with the even numerators. Right? For those fractional ones where the fraction is less than 1, you have no gradient defined here because you've got a cusp. But if you go where this exponent is greater than 1 for these beasties, like x to the 8 over 7, x to the 10 over 7, and x to the 12 over 7, well, then you get this downward sloping graph, hanging under the line y equals x here and hanging under the line y equals x over here, hanging progressively more as the improper fraction gets more and greater than 1. You get this effect here, and all these curves, even though they mightn't look like it, for example, that pink one, it looks very, very sharp and kinky down there, but if you get a magnifying glass and have a look around the origin, it's actually steep, but it's smooth. So they're all smooth. These ones where the exponent is greater than 1 with an even numerator and an odd denominator, they're all smooth and the gradient is defined. Wow. I know. It's just almost too much, isn't it, all this? Now, forget all that. Oh, don't forget it, but I mean, for now, we're just going to move on to reciprocals. These are the easy ones. This is the y equals x over n, where n is p over q, remember, any rational number, but p over q is negative. In other words, it's x to the 1 over x to the p over q positive version. Yeah, so they are the reciprocals and they're easy to work out. First of all, you draw the graph of y equals x to the positive exponent. I've written it as a modulus thing. It looks a bit beastly, but it just means the positive exponent version of what you've got up here when you've got a negative exponent. And basically, that is with the positive version of p over q as already described, and what you then do is you draw the appropriate reciprocal based on this curve with the following guidelines. When the original function is positive, the reciprocal will be positive, of course it will. When the original function is negative, well then the reciprocal is going to be negative. When the original function is 0, the reciprocal will be undefined or infinity, plus or minus infinity, depending on whether the original function is approaching 0 from the plus direction or the minus direction. What else? When the function is very large, the reciprocal is going to be very small because you're dividing. If you're dividing 1 over something very large, becomes very small. See? The reciprocal likes to play the game of opposites. And when the function itself, the original function, is very small, then 1 over it, the reciprocal, is going to be something over 1 over something very small, which becomes very large. Now, lastly, but very importantly, when the function is plus or minus 1, the reciprocal will be 1 over plus or minus 1, which is plus or minus 1 respectively as well. Okay? Get that? Well, if you don't get it, don't worry, here they come. Now there's the graph of y equals x. Now, 1 over x is going to follow all of those rules. The reciprocal, or y equals x to the minus 1. What did I say? You draw the graph of y equals x to the plus 1, and then you basically get the reciprocal, which is y equals 1 over x or y equals x to the minus 1, by using all those rules. They'll pass through here, and it'll pass through there. This side of the graph will be positive. This side of the reciprocal graph will be negative. Where it's very small, the reciprocal is going to be very large. Where the original is very large, the reciprocal is going to be very small. When it approaches 0, you're approaching an asymptote. That'll be from the positive direction, asymptote. This will be from the negative direction, asymptote. That's approaching plus infinity. That's approaching negative infinity. And here it comes. Ready? Are you ready? Are you ready? Ready, set, go. Look, exactly what I said has come true for me and you. Now, are we ready to go on? X squared. Now, if you follow all those rules, you might want to pause the video and have a go at it yourself, but I will show you. When I say ready, set, go, it's the go is when I'm going to reveal it, all right? Ready, set, go. There it comes. Look, isn't that exciting? That's a truncus. If ever I saw it, that's a truncus. Now, here we go with the next one, x cubed. Now, come on, in your mind, what do you think that reciprocal is going to look like? Have you got it? Have you got it sketched out in your mind? Give that brain of yours, that magnificent brain, some exercise and get those little neurons firing and the synapses connecting, because that's what that practice does for you. Here it comes. Ready, set, go. There, did you get that? Oh, very good. You got that. That's terrific. Now, we're going to do now, this is a bit interesting, x to the 1/3. Look, the principles are still the same, guys. work it out in your mind. What do you think the reciprocal would look like? Okay, x to the minus the third, or 1 over x to the third. What do you think it might look like? All right, I'm going to reveal it to you. Ready, set, go. Ah, that's what I thought. Is that what you thought? Good, good. Oh, well, we're cooking along very nicely. Last one here, last one before we go and have a nice cup of tea. This is y equals x to the half, so we're looking for y equals x to the minus a half, or y equals 1 over x to the half, and the same principles apply, exactly the same principles apply, and I think you know by now what it's going to look like. So I'll reveal it to you on a ready, set, go. Ready, set, go. There it is, don't you know? Yes, it's marvellous. And that's the end, I think. So there's the trends. The trend is your friend, and this is how it all works. And I hope that's been a clear and a step-by-step and detailed explanation of what these graphs look like. It helped me tremendously working all this out, because I was very confused when I first saw all this stuff just thrown at me in a textbook, but now I really feel I do understand it, and hope you do too. So we'll see you next time. Oh, I've got to reveal the star, because you're a star, huzzah. And we'll see you in the next exciting video. Okay, bye for now.